Alright, so let's talk about differential calculus. I'll try to be pretty quick here. So first of all, what's the basic definition? A derivative at a point, right? The idea is to capture the slope of the tangent line, right? So what we do is we fix a point A, and then we look at another point, A plus H, and then those give you corresponding points on the graph, right? Like I've drawn here. And then the slope, this line which connects these 2 points is called the secant line, right? So this secant line this is the slope, right? It's the change in y, the rise over the run, over the change in x, right? And then as we allow this h to get smaller and smaller, we get, our secant lines get closer and closer until eventually we home in on this very special line that's known as the tangent line. Now, that presupposes, of course, that this limit exists, right? There are, of course, it's not hard to come up with functions which don't have a well-defined tangent line at the point, right? But if the tangent line does exist, then that means this limit exists, and the value of this limit at the point A is the slope of the function at A. It's called f prime of A. Of course, if we do this for a bunch of points at once, we define what's called the derivative function, right? So if we say A maps to f prime of A for each A in, let's suppose that this function is such that it makes sense at every point, okay? But generally speaking, the domain of the derivative could be smaller than the domain of the function, of course. Well, that defines a new function called the derivative function, right? And so you spent a lot of time looking at these difference quotients and seeing how they work last semester. Anyway, just, the basic thing we must know, definition, the equation of the tangent line, if it exists, all right? I mean, there's different ways to say it. I could say at the point A comma f of A. Sometimes I would say find the tangent line at x equals to A, however you want to think of it, but is given by y equals to f of A plus f prime of A times x minus A. And there you go. This, folks, is a simple formula for the tangent line. If I ever ask you to find the equation of a tangent line in Cartesian coordinates, it's as simple as this. You calculate the derivative, you plug in the point, and there you have it, all right? So let's see here. For example, if we had f of x equals to, say, the square root of x, right? And we want to look at, now of course there's another way you can write this, right? You can equivalently write this, the limit as x goes to a of f of x minus f of a over x minus a. These are the two competing formulas for the slope of the tangent line, or the value of the derivative at the point, if you prefer. So which one of these is better for a given problem? I don't know, depends. For this particular example, I prefer that way of calculating the derivative. So f prime of a is the limit, right, as x goes to a of the square root of x minus the square root of a over x minus a. All right. But if you use your imagination, you can see that that is the limit as x goes to a, right? Square root of x minus the square root of a over, well, this is, what is this? This is the difference of perfect squares. Can you see it? Square root of x squared minus the square root of a squared. Here, of course, we're assuming that a is positive, all right? Otherwise, this limit won't exist. Anyway, so there you have it. This is square root of x minus a, square root of a rather, times the square root of x plus square root of a, factoring right? Now, x goes to a, but it doesn't reach a in the limit, which means we can reduce these, they cancel out, and we're just left with the limit as x goes to a of 1 over the square root of x plus the square root of a. And then this function is unambiguous. I can just plug in the limiting value, and there it is. Square root of a plus the square root of a, 1 over 2 square root of a. So we have this then. F prime of x is equal to 1 over 2 times the square root of x for this function, right? Now, thankfully, we don't have to keep doing this limiting stuff forever, right? We can instead look at this as like df dx is our other notation, right? Okay, more on that in the next page here. But let me just before I forget, let me just what's the graph look like? What's the equation of the tangent? Let's just see how this works for just a second here. So all right, so the function, this graph is half of a sideways opening parabola, right? And if I wanted to find the tangent line, say at some point here, let's say, to keep it simple, let's say this is the x equal to a equals to 4, basically, all right? So to find the slope of the tangent line at x equals to 4, what is it? Well, the slope of the tangent line is f prime of 4, right? So f prime of 4 is 1 over 2 times the square root of 4. Sorry, it's getting kind of cramped here, but it's 1/4. So there you go. The equation of the tangent line is the value of the function here, which is what? That's 4 comma square root of 4, which is 4, 2. So I do y is equal to 2 plus 1/4, all right, because that's the value of the derivative, times x minus 2. Oh man, sorry, contrast of white on white and all. It just so happens that oh, I'm an idiot. Not 2 here, right? What's wrong? That shouldn't be 2. That should be what? That is a 4, of course. That's the x value is there. All right. So there you go. Equation of tangent line. I mean, the equation of tangent line should be an equation of a line. If you have a 1 over 2 square root of x here, you do not know what you're doing. And it's easy for me to see. I'd rather you knew what you're doing, though, of course. All right, so anyway, that's the basic geometry. Is the derivative tells you the slope of the tangent line, of course. Then operationally, the question is, how do we calculate them? That's the primary thing you need to, like, so how to calculate derivatives is really the larger question, and I guess you could argue the more important question for calculus, too. All right, how to calculate derivatives, right? If you can't differentiate, you can't integrate. So let's see here. Let's just go down the basics. So first of all, we prove that there's something, well, first of all, there's linearity, right? So if you take the derivative of f plus g, you've got df dx plus dg dx. Or if you like in prime notation, f plus g prime is equal to f prime plus g prime. Got to be careful with the prime notation. It is efficient, but it can also be confusing. But anyway, there it is. Now, if we have a constant, right, then we can pull it out. In the prime notation, that looks like this. Cf prime is equal to Cf prime. Product rule, right? ddx of a product is df dx times g plus f times dg dx. All right, in prime notation, that's f times g prime is equal to f prime g plus f g prime. There's also a triple product rule, which I'll only write in the product rule, in the prime notation. Fg prime, fgh prime is f prime gh plus fg prime h plus fgh prime. And I think you see where this is going. I mean, you can keep doing that. All right. Quotient rule. Well, ddx of f over g, right, is, well, it's df dx times g minus f times dg dx. The minus goes with the derivative of the denominator function divided by g squared. Or, if you like in the prime notation, f over g prime is equal to f prime g minus f g prime divided by g squared. All right. Hopefully this is your happy place. I mean, I would hope. What I'm about to write, of course, gives students more trouble. The derivative of a composite, right? d dx of f of g of x is what? Well, it's df dx evaluated at g of x, right? Times dg dx. Now, there's another notation we can use for this to be more precise, more concise, I should say. You could just say df dg times dg dx. It almost looks like we're multiplying by 1, but you should understand that that's just a slick notation. Now, in prime notation, f composed, that circle is not optional. You must write it, because there's a big difference between this and that. That's a product, this is a composite. But f composed of g prime is f prime of g of x times g prime of x, all right? That's the chain rule, right? So these are the foundational facts of differential calculus. You must know these, you must apply these. Now, added to those, of course, we have, derivatives, basic derivatives. Now, when I teach Calculus 1, I will derive these from basic principles, from limits. But for our purposes here, I'm just going to state them and show you how it works, all right? So, first of all, d dx of x to the n is n times x to the n minus 1, the power rule. And this is true for n in the reals. Kind of neat. All right, the other thing we should know, of course, derivative of e to the x is equal to e to the x. The derivative of sine x is cosine x. The derivative of cosine x is minus sine x. All right, what else do we know? The derivative of tangent x is equal to secant squared x. The derivative of cotangent x is equal to minus cosecant squared x. The derivative of secant x is secant tangent x. The derivative of cosecant x is minus cosecant cotangent, I believe. Let's see here, what else do we know? The derivative of cos x is sinh x. The derivative of sinh x is cos x. All right. Anything else basic I've left out here? So these, you just need, I mean, you really should just know these. I mean, I can derive, honestly, probably just these I really need to know. If I know these, I can derive the rest, but you don't want to have to derive these ones in the midst of other things. I mean, you should know how in case you forget, but it's nice to know if you haven't. In like fashion, d dx of the natural log of x is 1 over x, right? d dx of a to the x is the natural log of a times a to the x. Let's see here. Now let me talk more about, so those are your basic ones, you need to know those. Let's derive, how to, let's say how to derive in a pinch. Suppose you forgot what the derivative of hyperbolic tangent is, like me. Well, no problem. We know the quotient rule, right? And we know the derivative of sinh and cos, so this is what? This is the derivative of sinh x times cos x minus sinh x times the derivative of cos x divided by, cos squared x. All right, so that is cosh squared, because that's cosh times cosh. Derivative of sinh is cosh, derivative of cosh is sinh. It's just like sine and cosine, except all pluses. Interestingly, though, there's a minus in the so-called, like the analog of the Pythagorean identity for hyperbolic sine and cosine, which is super handy here, because, hey, that's 1. So we get 1 over cosh squared, right, which, of course, is hyperbolic secant squared of x. All right, so therefore we have the identity, d dx of hyperbolic tangent of x is equal to hyperbolic secant squared of x. All right, now, I think you guys can probably, these reciprocal derivatives aren't too bad. It's just quotient rule, right? What we'll sneak up on you guys more is the derivative of inverse functions. You may or may not have seen that in a previous class. I think we pretty much start with that. So let's just talk a little bit on derivatives of inverse functions. Now, once I finish up with this introductory stuff, I'll do a few pages of just gory combined differentiation things. Interest, what's wrong with me? Inverse functions. So it's pretty much the same song and dance every time around. So let's start with, for example, you have f of x is equal to natural log of x, all right, for x positive. So to find the derivative of this, suppose you don't know it, all right, what we do is y equals ln of x, all right, then I take the exponential of both sides. E to the y equals to e to the ln of x, right, which is just x again. So there you go, I've got e to the y is equal to x. Now, what I do then is I differentiate both sides, and I use the chain rule. Y is a function of x, right? So that means that I have to do, take the derivative of both sides. d dx of e to the y, right, is equal to d dx of x. Well, that's just 1, right? So we get e to the y times dy dx. Notice that the dy dx has to be there because we're differentiating with respect to x, a function of y. So this chain rule applies. And this is equal to 1. So, lo and behold, we have dy dx is 1 over e to the y. But wait a second, e to the y, you will recall up here that that's exactly 1 over x. And there you have it. d dx of ln of x is equal to 1 over x. And so that's how to derive the derivative of the natural log, if you, for example, forgot it. But I would recommend that you just know the derivative of natural log is 1 over x. I mean, that would be a wise thing to commit to memory. Let's see here. Another example of this flavor, which is going to be rather different, is f of x equals to inverse tangent of x. All right, suppose I want to find the derivative of inverse tangent. It's basically the same song and dance. Y equals inverse tangent. All right, I take the tangent of both sides. Tangent of y is equal to, equal to x, because tangent of inverse tangent is just x again. I differentiate both sides. So differentiating gives me secant squared y times dy dx, because I'm differentiating with respect to x. All right. Again, chain rule applies over here because I'm differentiating function of y with respect to x. So dy dx is, after all, what I'm after, because I want to know what's, I'm saying y equals inverse tangent of x. What's the derivative of inverse tangent of x that we're trying to figure out at the moment? So dy dx is 1 over secant squared y. Aha! But I remember just a few minutes ago we derived that secant squared is 1 plus tangent squared. Right? But what is tangent? Well, tangent is x, right? So there you have it. d dx of inverse tangent of x, right, is equal to 1 over 1 plus x squared. So that's how we can work out the derivative of a inverse function. Basically what you do is you say y equals to the unknown, the function whose derivative you don't know, you use the function, the inverse of the inverse function, the function itself, in this case tangent, in this case exponential, that converts it to an expression where you know the derivatives, right? And so you can figure out what the derivative of the inverse function is. It's a little bit off topic, but I feel like I'm honor bound to share this with you. So if you look at it, generally speaking, right, f of f inverse of x, or you could, I mean, whatever, equals to x, let's say, all right? If I differentiate this, the chain rule says what? It says df dx, right, at f inverse of x times df inverse dx is equal to 1. Or you could write it this way. F prime of f inverse of x, all right, this is kind of getting a little bit hairy here, times f inverse prime of x is equal to 1. Well, this is a fascinating equation because what this says is that if the function, right, if the function's increasing at the f inverse of x, then the inverse function must also be increasing at x. So like if you pair x with f inverse of x, or if you differentiate the other thing, which would be like f inverse of f of x equals to x, you could differentiate that, then that would give you df inverse dx at f of x, right, times df dx equals to 1. So what this says is that the rate of change of the function and the rate of change of the inverse function have to multiply at corresponding points, right, matching f of x with x. They have to multiply to give you 1. That means that they have to be reciprocal. That means that the rates of change of the inverse function and the function at corresponding points, as I'm describing here, they have to be both positive or both negative, right? So like, check it out. For example, this one that we just worked out. Remember the graph of tangent? Remember what it looked like? It was increasing everywhere, right, wherever it's defined. And you know what? The inverse tangent, 1 over 1 plus x squared, well, that's positive, right? So the function's increasing, the inverse function's also increasing everywhere. Likewise, the exponential, right? Exponential is everywhere increasing. Think about its graph. The derivative of the exponential, the natural log 1 over x, that's also positive. It's no accident, all right? So if you have a function which is decreasing, for example, like cosine, right? Suppose you wanted to find the derivative of inverse cosine of x. Well, remember, inverse cosine is cosine is what? Cosine is like this. That's the part of cosine which the inverse cosine is the inverse of, right? It's the inverse for cosine restricted to that bit, and cosine is decreasing on that branch. And so if I go through this same song and dance, I have, cosine of y is equal to cosine of cosine inverse of x, which is x, right? Differentiate implicitly with respect to x, we get minus sine of y dy dx equals to 1, right? And so that gives me dy dx is equal to minus 1 over the sine of y. Now, sine of y is what we want a formula in terms of x, right? So logically speaking, you think about it, we know that cosine squared y plus sine squared y is equal to 1. That tells me that sine squared y is 1 minus cosine squared y, which of course is 1 minus x squared in this context. So algebraically, this says that the sine of y could be plus or minus the square root of 1 minus x squared. So how do I know which to choose, the plus or the minus? Well, the answer is clear. The square root, the output of the square root is non-negative. At worst, it's 0. It's usually positive. I'm forced to choose the plus because I've already got a minus here. In other words, dy dx has to be equal to minus 1 over the square root of 1 minus x squared. Why the minus? Because the derivative of the cosine should be negative everywhere, because the cosine is decreasing everywhere the inverse function is defined, right? So that's it. And there you have it. d dx of inverse cosine of x is simply equal to that. All right. Now, if you watch the lectures from last year, I think the first few lectures I was working out this stuff, but I've decided to start a little bit further in integration because when I did these things in class last semester, they didn't really work out that well, and I really am more interested in integration, so I'm just trying to more relegate this to it's stuff you should know, right? But I'm going to try to focus more on integration at the start of this semester. All right, so there's a little bit on inverse functions, and I'll do more differentiation in the next video. Thanks, guys.